Today, we'll walk through a demo of Rescale's compute, data, and AI products. Let's start with the user experience of a fictitious thermal engineer, Alice, working on a new Acme electric vehicle. Her goal is to optimize the heat dissipation efficiency of a new heat exchanger. Alice is first logged into Acme Automotive's existing workspace for their electrical vehicle battery project. Here, we're going to see all of the active products that Acme Automotive was working on, and specifically, Alice is focused on the Project EV Battery 4079. The first thing Alice does is plan her study. A study is the central entity that captures the full context of simulations being run, and it preserves the why behind the work by centralizing objectives, documenting updates, and capturing learnings. This becomes the single source of truth for Alice's work. So what she does is she creates a heat exchanger study by clicking New Study and then typing in heat exchanger, thermal efficiency. And this is under the Project EV Battery 4079, where she adds objectives and assigns herself. Within a study, Alice can see everything as a whole picture of everything that's happening. She'll see the description, whatever we're working on, herself as the owner, and the current status that's happening. But next, now that she's in a study, the next part is the core of Rescale, where it's running simulations or jobs. And there's a lot that happens behind what a job is. Just as a car simplifies its propulsion complexities, Rescale makes cloud infrastructure invisible. This includes compute optimization, region load balancing, multi-cloud integration, and software lifecycle automation. What Alice is trying to do is she's trying to run a series of thermal simulations to optimize the heat dissipation efficiency, document the results. So what she does is she goes into the study, into the Jobs tab, clicks New Job, where she'll create a job in the study. Once she creates a job within the study, she can go through and set up this specific job. We'll call it design as the first iteration. She'll add files from her computer from cloud storage, assign a software, and in this case, we'll assign COMSOL multiphysics. She'll go ahead and select the hardware appropriate for this specific simulation. As she assigns the hardware available, then she'll go through and select whatever is the right hardware for this. In this case, she can scroll down and see a variety of different hardware. Previously, we used CAD/CAM Max, but we also have the option of using core type sets as well. Core type sets can be used to streamline the simulation. Instead of strictly focusing on one type of hardware, if it falls over or if there's more optimal to start faster, it will go through the core type set to determine what is best for the job. Alternatively, we can use Rescale's compute recommendation engine to use the recommended hardware. And in this case, it's Rosenite. So let's go ahead and select Rosenite as our top hardware. Next, we'll use our automation capabilities. Automations will automatically extract our simulation results as it becomes available. So let's go ahead and submit this job. Once we submit the job, it will start in about 30 seconds. As simulations run, the cloud file system, Rescale's shared storage, intelligently captures and organizes the resulting data. Cloud file system acts as a shared knowledge hub. It enables Rescale users to collaborate seamlessly across the data. What is amazing is the cloud file system maps this exact same hierarchy that you see in the left-hand side. So whatever hierarchy you're seeing, you'll see the exact same thing in your file system. Additionally, if we open up a Rescale job, Alice can access these result files by simply downloading them directly from the UI by selecting all of the files in this page. Additionally, using the cloud file system, she can access these between workstations, jobs, and even on her local side to quickly download and interact with the resulting files. While raw storage captures files, we also need a way to transform them into parameters that engineers care about. We have automations, which extract and capture critical metadata. like simulation inputs and key findings, automatically enriching the simulation and study with valuable context. This creates a living knowledge base that evolves with a project, forming a digital thread. Simulation parameters such as peak temperature, pressure drop, and peak stress are automatically extracted from the jobs that Alice ran using automations. In addition to the context and input parameters are added prior to a job submission or afterwards. As these parameters are being captured, they can be used for ease of use in post-processing after the job is run. And once these parameters are captured, engineers need a way to explore, analyze, and share those findings. Rescale Data provides a suite of tools, including tools to create and compare results, AI-powered search to find information across your simulations and metadata, and in-browser visualization for rapid post-processing with Rescale. Alice goes in to our Data Explorer to analyze the best design candidates. So we'll navigate into the Design Explorer. As we jump into the Design Explorer, Alice gets to work through and analyze the best design candidates. In this case, Alice looked through all the design candidates to check between max temperature and max pressure drop with peak stress annotations to compare the various different results. In this case, she's optimizing for a low temperature and low pressure drop. And in this case, she's going to select this design 7. Once Alice finds the best design candidate, she's going to inform Bob, a structural engineer working on the battery integrity, through a comment within the study to keep him in the loop. So Alice will go back into her study. And once she's in her study, she can keep Bob in the loop by mentioning him in the comments. Alice's work is done on the optimization of the heat exchanger, but something in her head tells her that it can be better. Rather than continuing to iterate with expensive physics-based simulations, she decides to train an AI model using the data she generated in the study. As you can see, she has a bunch of design directly in the study. So what she does is she trains this AI model by simply going into the AI tab within the Rescale study. This turns every simulation engineer into a data scientist with the ability to leverage the power of AI. Alice goes to the study, clicks on the AI tab, which guides her through creating an AI model using her engineering knowledge rather than data science knowledge. She leverages the heat exchanger simulation data to train a model with the goal to further optimize our model. This process first processes the simulation data, second, trains the model, thirdly, deploys the model, and then fourth, as new simulation data becomes available, the model is automatically fine-tuned. This is then added back into the software catalog as a tile for Alice to leverage. So once the model is trained, Alice can go in and use this model to optimize her heat exchanger, either going forwards or backwards by using the input or output parameters as the goal. To do so, she clicks on New Job. As she creates a new job, you'll see we can create an AI simulation. I'll go into the software where we'll add AI. And then what we'll see is we'll be able to leverage the newly created model that we just built. In this case, we're using Rescale's in-house solver, Rescale AI Physics software. She can use these in jobs or workstations or visualize them directly. And once AI predictions are generated, validation is the key to ensuring accuracy. So Alice runs the simulation, finds an optimization, then reruns her COMSOL simulations to validate that the simulation is accurate. And also, AI models are also used for not only design optimization, but also for maintenance in the field. So as soon as we release this heat exchanger to the field, we'll keep the AI model for any maintenance or validation going forward. And this concludes our demo for Rescale Data, AI, and Compute.